will start the seminar. Thank you for joining us today on the Astrophysics Cosmology joint seminar for our two small groups at the Center for Theoretical Physics. And today we are having a remote guest, Akshay Singh, who is a last year PhD student at the University of Bar-Ilan in Israel. He works there under supervision of Professor Asaf Pir, and he will show us the results from his recent works. I just want to advertise also that Akshay was here in Warsaw last year at our conference about GRMHD simulations, and besides that, he has expertise also in observational astronomy because of his master's degree, which he did in the University of Mumbai in the X-ray astronomy group of Sudhi Bhattacharya, right? So yeah, warmly welcome you, Akshay, and I hope you will be able to tell us the full story about your radiatively cooled, magnetically arrested accretion flows. Please start.
So thank you, Professor Agnieszka, for inviting me for the talk, and thank you all for attending. Today I'm going to talk about how is the radiative cooling shapes the accretion in magnetically arrested disk. So feel free to interrupt at any time. So there's no problem with that. We are very used to in here. So what you see in here is just a representation of a black hole accretion disk, which is just a simulation picture of the one in the middle is a black hole with an accretion disk and a jet launching from that. So just a simulation that I made, and this is just 3D picture of that simulation. And I work with my supervisor, Professor Asaf Pir, and kind of my co-supervisor, Dr. Damien Begwe. And both of them are the co-author of the paper I'm going to describe. So the outline of my talk would be a brief introduction to accretion disks. And then I'll describe about the numerical simulations and why do we need to perform the numerical simulations, and a little bit about our own code, that is cuHARM. And then I'll try to tell you why is the need to study the radiative cooling and what are the impacts of radiative cooling on accretion disks. Then I'll describe my analytical and numerical results. And the summary and conclusion will follow from that. So for those who are not aware of the accretion disk, so on a very basic overview, an accretion disk is a rotating structure of plasma formed around the compact objects such as the black holes and neutron stars. They are known to power some of the most luminous phenomena, for example, the gamma ray burst, active galactic nuclei, and others. And a very important factor that is influencing the dynamics of an accretion disk is the mass accretion rate, which means that how much is the amount of matter which is flowing towards the black hole. And the second is the magnetic field, because magnetic field plays a very important role in the transport of the angular momentum through the magnetorotational instability. Otherwise, the matter because the matter has a certain angular momentum, in order for it to move towards the black hole, it needs to lose the angular momentum, which happens through the magnetorotational instability. And the magnetic field plays a very important role in that. Now, when we study the black hole accretion disks from the numerical simulation point of view, we differentiate the accretion disk into two regimes. The first one is called as a standard and normal evolution, that is the same disk. And the second one is the magnetically arrested disk, which is called mad accretion disk. And one of the way of differentiating between them is by the plasma beta parameter, which is written here as the ratio of the gas pressure to the magnetic pressure. And what you see from the picture on the bottom is that when the plasma beta is very high, that means the gas pressure is very high, and comparatively the magnetic pressure is very low. The gas flows of the matter which is flowing towards the black hole, it flows very normally in a very streamlined pattern. However, when the gas pressure is low comparative to the magnetic pressure, or the magnetic pressure is high and the plasma beta parameter is low, But what it leads to is because of the plasma has a property of frozen in magnetic flux. So it brings the plasma, so the plasma brings in the magnetic field with it. And what happens, a certain amount of magnetic field is built up onto the black hole magnetosphere. And after which it becomes so strong that it somehow impedes the accretion. And in that case, the accretion does not happen like very smoothly in the streamline flow that is shown on the left, but rather it happens through the magnetic interchange instability in the form of kind of a blobs-like structure which flows towards the black hole. Now, since my work is mostly related to the magnetically arrested disk, I will not talk about the same disks from here. So the little introduction about the magnetically arrested disk. So in magnetically arrested disk, they have a very strong magnetic flux near the black hole horizon. And the black hole, the magnetic fields become so strong into the mat that it regulates the mass accretion that is happening towards the black hole. And two of the very key features of a magnetically arrested disk is that it shows the variability due to the magnetic flux eruption. What is a magnetic flux eruption? I will tell you in the next slide. And also, another property of a magnetically arrested disk is the formation of a powerful jets using via the Blank-Fuznak process, which can have an efficiency greater than the 100%. And that efficiency greater than 100% comes out at the expense of the spin energy of the black hole. Now,
so can I ask one question already at that stage?
Sure.
So on your previous plot, you mentioned, yes. Eddington ratio 10 to minus 6. So
yes.
Is this true that this magnetically arrested disk model or process really applies only to low Eddington ratio sources, or this is just assumption for convenience, because then you can assume optically thin medium?
No, actually, it applies to all the mass accretion rate. Even for the super Eddington mass accretion rate, it does apply. What I'm showing in here is just as a representation of what is a magnetic flux tube. So the blue regions, the dark blue regions, and those like yellowish region, which are the plasma accretion funnel, which is carrying the matter towards the black hole. In our work, we mostly perform the simulation to sub-Eddington accretion ratio, which I will tell you later why, because we did not do the 2-temperature plasma simulation, but that we can discuss later. But it also applies to the super Eddington accretion rates as well. Here, this is just for a representation purpose.
Amit has a question.
Is the disk magnetically arrested or a part of the disk is magnetically arrested?
So, well, when I describe a magnetically arrested disk, so it all comes down to, so here we are describing about the numerical simulation output that we get from a magnetically arrested, what we call as a magnetically arrested disk. So the basis of defining a magnetically arrested disk is the large amount of magnetic flux being accumulated onto the black hole magnetosphere. So it depends on your resolution and how long you are running your simulation will determine up to what distance in the disk your disk will remain in the MAD. So it's not like the entire disk is MAD. It is the inner structure of the disk which will be MAD. So if I perform a same simulation of something like 200,000 M, my disk will be in the MAD state up to several hundreds of M. But what I have performed in my simulation, the disk is in the MAD state up to a radius of somewhere around 50 or 60 RG. So it is only the inner region of the disk which will get highly magnetized, and all the magnetically arrested behavior that you see here. This picture that you see here in front, I think I'm plotting plus minus 25 RG from the origin. So this is just a 2D picture of a simulation. I believe people may have seen it. So what you see in here is this just a 2D picture of a black hole accretion. One is from the front on view of an observer, and the one is from the A's on view as from an observer, which is looking downwards towards the black hole. And what important thing that you start seeing in here is those blue regions that you see. These are what I call as a magnetic flux eruption. which I will tell you. So these are the magnetic flux eruption tube that you see from this 2D view. So I'll go ahead with that and then, oops, yeah. So what is a magnetic flux eruption? So in so as I said earlier, in the plasma has a property of frozen in magnetic flux. So it brings in the magnetic flux along with it, and that magnetic flux accumulate onto the surface of the black hole horizon. So if you look at the plot on the left here at the bottom, what I'm plotting in here is a parameter called as a MAD parameter, which is basically a ratio of the magnetic flux at the horizon and is normalized by the square root of mass accretion rate. So initially, when there's no accretion occurring, the magnetic flux was at the black hole horizon was 0. When the accretion starts, the magnetic flux at the horizon continuously increases, and until it reaches to a saturation point, after which the magnetic flux onto the surface of the black hole cannot accumulate anymore. Because of that, what happens is that so if you know the picture of a I don't have the picture at the moment to show, so it's like this is my black hole. The magnetic field lines are like this and like this on the top and bottom. But when the magnetic flux becomes so strong, those magnetic field lines will become very close to each other and they will reconnect. And because of those reconnection events that you see, those blue regions appears, which are basically a very highly magnetized region that are formed when the magnetic field reconnect and a large amount of magnetic energy is being thrown outward into the disk. So during that event, what happens is the magnetic flux reduces, and then again the accretion restarts and the magnetic flux builds up again. And this process repeats during the accretion multiple times.
And what is shown by the color scale in your map?
So these ones?
Yes.
So these blue regions are the ones which are the magnetic flux eruption events, which has a very high magnetic energy density. So this is the density
magnetic
plot.
Energy density,
No,
or
this is just the density plot. This is just density. This is just density. Here you see that the density is very low, and the outer region the density is very high. So in this region the density is very low, but magnetic field is very strong. Okay, so for those who are not into coding much, this might not be very much relevant, but I think it is good to describe about our code. So I'll describe in a very few words about our code. We have our code, which is named as a cuHARM. It is basically a more advanced version of the cuHARM code, which was written by Professor Gami in 2003. So it is a 3D GRMHD code, which uses the finite volume method to solve the GRMHD equations, because GRMHD equations are partial, like coupled partial differential equation. So there is no analytical solutions to them. It uses the flux constraint transport to preserve the divergence of B equals 0. That means no monopole constraint. The most important part is it is written in CUDA C. It uses the GPUs for the acceleration, and it also uses OpenMP and MPI for the parallelization. Now the reason for using a GPU is shown in here. So just the reason for using GPU I saw in here. So what you see from the picture in here is that I'm comparing the compute throughput that I get when I compare an Intel Xeon 80 CPU compared to a 8 NVIDIA A100 GPUs. So there is a clear difference of 33 times more compute output that I can get if I use the GPUs for the acceleration of the codes rather than using the CPUs. However, it comes at the expense of writing tremendous amount of code and optimization, which requires a lot of effort and is mostly written by my co-supervisor, Dr. Damien Begwin. Mostly it is by him, and we other also use it and modify it according to our use. And it is designed for using multi-GPUs, and it can have the more than 100 million cell updates per second on H100 cards. But that also depends upon the kind of problem we are studying and also the number of cards that are available on nodes. Okay, so here is a rough output of the compute throughput that we get. So here I'm showing the result of the number of cell updates that we get for an NVIDIA H100 card. So you can clearly see that they are close to around 220 million cell updates per second on an H100 card. On the right-hand side, what I'm showing is something called strong scaling in the language of computing. So what strong scaling means is that you have some task to do which you want to do on GPUs. Now, if I increase the number of GPUs onto the same nodes and I keep the size of the problem same, how is it going to improve or not improve the ability of the GPUs to solve the problems? So here we use the strong scaling for a resolution of 512 to 56,512. And what you can see is that in up to 8 GPUs, so 8 number of nodes, we get a very high strong scaling. But after that, the scaling starts to become little less. And the reason for that is that if I use a 512, 256, and 512 as a resolution, after the node of 8, the amount of work that is allotted to each GPU becomes very less. So that means that most of the GPU time is being just stable and not doing anything. That is the region that you see is that strong scaling starts to diverge. If I use instead of 512 and like 1024, we get strong scaling up to 32 nodes of the H100. Okay.
And may I ask, your code is parallelized in all the 3 directions, or
yes,
only in one?
No, in all the 3 directions. Okay, so what do we use it for? Because it's an advanced state-of-art sim code. However, the worst part of is that it is very complicated, and we run 2 versions of it. So one is a highly optimized and easily modifiable version, like 2 versions. We modify first the easily modifiable version, and depending on now the compute output, we increase the optimization and use it for studying the equation disks. Now, this is the slide which might not be very helpful for some people who don't like equations, but these are the equations that we are trying to solve. So the first equation is just simply the equation of conservation of number density. Second one is the equation of conservation of energy and momentum. And the third one is the Maxwell's equation. What you see is an extra term that I have used into the equation of conservation of energy and momentum. Here, this term capital lambda is what I call as a physical cooling. And in our simulation, we use the physical cooling in the form of Bremsstrahlung and synchrotron cooling. And the form of electron ion and electron Bremsstrahlung cooling is given by this formulas, and the synchrotron is given by this. Now, a very important thing is that we neglected the Compton cooling because it requires the information about the photon field, which is in some cases it is available by 2 different methods, but it is not very well known. So we decided to not include the Compton cooling. And also to perform the simulation, we use a model for the electron temperature, like how is the electron temperature associated with the proton temperature. Therefore, we decide to work with the temperature ratio such that the electrons and protons are tightly coupled, whereas the proton temperature is 3 times the electron temperature. And it also requires us to set a physical unit of problem, like what is the mass of the problem, what is the mass of the black hole that we want to use for the targeting mass accretion rate. Therefore, we decided to use with the mass of the Sagittarius A star, which is given from EST results. Now I come to the main motivation of my work. So what is known is that from the previous works that the radiative cooling changes the structure of the disk and dynamics, but like why, but up to what, how much, and what are the modifications that are changes into the disk is not very well known. However, there is one thing that is very well known is that the synchrotron cooling dominates at the low mass accretion rate. Now, we wanted to understand, so there is let's see that if I have to perform a GRMHD simulation, whether do I need to include the radiative cooling or the radiation into the simulation or not? Because most of the simulations that are being performed into the domain of GRMHD does not involve the radiation, because radiation is quite expensive. So we wanted to understand up to what mass accretion rate the radiative cooling is not important, so we can simply neglect it, and after which we have to include the radiative cooling. Otherwise, we are losing some of the impacts of radiative cooling on the dynamics. Now, if there is such thing exists, what is the critical mass accretion rate above and below which the mass dynamics changes? And if there is a existence of a such mass accretion rate, how would it impact the overall structure of disk, balance forces which are balancing the disk, and the efficiency of jets? So first we decided to perform some analytical estimates and then see if our analytical estimate match with the numerical simulation. So our analytical estimate is a very simple. So what we do is we look for a particular mass accretion rate where the cooling efficiently taps out the internal energy of the gas. What we use is that, so rate of energy law. So what happens is that the black hole or the accretion, because of the accretion, there is a potential energy gain and there is a rate of loss of energy through the synchrotron. Plus Bremsstrahlung, but why I did not include Bremsstrahlung, I'll describe just in a few minutes. So what we do is that we simply equate amount of energy gain to the amount of energy being lost. So what do you see in here is that this is the synchrotron formula, this is the gravitational potential, and this is the amount of matter which is flowing towards the black hole. Now we use the fact that the MAT parameter, that is the magnetic flux at the horizon saturate, it allows us to simplify the magnetic field. So what I can do is I can write the magnetic MAT parameter simply as the radial field divided by the square root of mass accretion rate with some constant. Now we apply a model of electron temperature that I said earlier. And after some analytical calculation, we get a value of a critical mass accretion rate, which comes out to be 2.8 times 10⁻⁶ Eddington accretion rate. Now here, A and alpha are the two constant, which depends what fraction of energy is getting into, like what fraction of energy is lost, like 50%, 30%, or the numbers. Okay, now what we see from in there is that, so what we expect is that when my mass accretion rate is above the critical mass accretion rate, radiative cooling should become dominant and it modifies the properties of disk. However, when the mass accretion rate is below, the radiative cooling is not a very significant, and we can remove it from the, we can perform a simulation even without including the radiative cooling.
I have a question here because you are assuming this constant ratio between proton and electron temperature, but as far as I know, many people use a more complex functions for that, depending on the plasma beta parameter. So how would this change your estimation?
So what I am using is this factor of electron to proton temperature of 3. And what people have been using is that so the values anywhere between 3 to 10. So, and I will come to this point at the end as well. So, and it is true that using a particular choice of electron to proton temperature is not 100% correct. So it is only correct into a certain regime of the mass accretion rate. If I go above a particular mass accretion rate or below, if we will have a certain problem, because if I go to a lower mass accretion rate, the Coulomb coupling is not that very strong. Therefore, we might overestimate the value of the radiative cooling. However, we decided not to go for the higher mass accretion either, because we realized that if we go to mass accretion rate more than 10⁻⁴ Eddington, in that case, the radiation backscattering will also start having an impact. Therefore, we decided to restrict ourselves into the region where our results will be more like robust, rather than performing simulations in the wide range where we know that it might not be very useful. So it is true that it will not be 100% accurate, but we have compared our results to the simulation that were performed, including radiations. And we found that our results vary by a factor of 2 to 3 by max, if including the 2-temperature plasma approximation. Okay.
Okay.
So now we have the analytical estimate. What we want to do is to perform the numerical simulation and to see if we see some kind of a change in the behavior of accretion disk. So we perform a large range of numerical simulations for the wide range of spin, starting from a highly retrograde to highly prograde spin. And we use a large magnetic field as an initial condition, because the larger magnetic field, we need a large magnetic field loop so that a large amount of magnetic field will be accumulated onto the surface of the black hole and leads to the formation of MAD. And we started with a mass accretion rate from -7 m.Eddington up to -4 m.Eddington. Now here I describe about my results. So I'll describe 3 or 4 of the main results that we see. So what I'm showing in here is again the magnetic flux at the horizon. So the plasma beta parameter. So magnetic flux at the horizon on the right hand side. So what you see from the picture is that when the when the spin is very highly retrograde, the phi b increases up until a particular mass accretion rate of -5, and then it starts decreasing. However, for a positive spin or a low and a high spin, there is the value of the magnetic flux is remaining constant, and then it starts to decrease. And there is a transition between these two regimes, like what happens into the higher mass accretion rate and a lower mass accretion rate happens in the region close to 10⁻⁻⁵ m.Eddington, which is in the same range as the critical mass accretion rate that we got from the simulation, that we got from our analytical estimate. Now, we decided to measure the jet efficiency. So the way we measure the jet efficiency at the horizon, it's simply 1 plus E dot. E dot is the amount of energy flux, which is moving towards the black hole, divided by the mass accretion rate, both measured at the horizon. A very important fact that we see from in here is that for a for the low spin or a negative spin, the value of the efficiency of jet is increasing and then starts to decrease slightly. However, for a very high spin, that is highly prograde spin, it initially increases and then starts to decrease. Here also we see a transition that happens and the mass accretion rate close to 10⁻⁵ or 5.5. And what we get from, what we see is that this is the kind of a theoretical prediction that we can get from our result, that at higher mass accretion rate, the efficiency of the jet should be quite low. So the jets are mostly more efficient when the mass accretion rate is low. At a higher mass accretion rate, jets are not as efficient as for the low mass accretion rates.
So for high accretion rate, Blandford-Znajek is not the dominant mechanism. Is this what you are saying?
So it would be a very strong claim to say that it is not very, that Blandford-Znajek is not very strong, not a dominant mechanism there. But what our results suggest is that the efficiency of the Blandford-Znajek mechanism will be lower compared to what it is for the low mass accretion rate.
Mm-hmm. Yeah, because normally people assume that it's proportional to the square of the spin, something like
yes, phi b square. Yes, exactly. The square of the mass, the magnetic flux. This is how it is being measured since long time. Mm-hmm. In the simulation, the way they measure it is by square of magnetic flux, but the reason is that we are getting the low magnetic flux that you get in here. So the low magnetic flux means directly proportional to the jet efficiency is directly proportional to magnetic flux square. If I have a low magnetic flux, the efficiency would also be going to low.
Yeah, but the question is, I think, about the spin of black hole, yes?
Yeah,
It's
because
also
Yes.
normally people
reversed.
try to measure the spin of the black hole just from jet efficiency, but you say that it's kind of degenerate for large accretion rates. So you cannot measure the spin from jet efficiency. Is that correct or it's not correct?
It's kind of a partially correct, but measuring measuring the spin of the black hole is kind of a very messy job at the moment, I would say. It is not very well resolved how well is the measurement of the black hole spin, but my results somehow suggest that the efficiency will go low if you have the higher mass accretion rate for slowly spinning black hole, or even for highly spinning, for any black hole, I would say. Okay, so next I describe about the disk height. So what is the disk height? So disk height is mostly the ratio of the height to the radius ratio that we measure for the disk. So for the time being, look only at the plot and the bottom. So here I'm showing the disk height that for spin 0 for a different mass accretion rate simulation that we target. So how is the disk height being measured is simply the considering the fact that the density is maximum into the mid-plane of the disk, and the density filaments or the density is equally distributed on the either side of the mid-plane of the disk. So what actually should happen is that cooling should reduce the disk height, because what happens in the cooling, because of the radiative cooling, the radiation means the disk is losing the thermal pressure in the form of radiation. And because of the disk becomes denser and thinner. However, what you see from the picture on the right, that it does not look like the very picture, because here you don't see that the disk height is decreasing if I'm increasing the mass accretion rate. Because what we expect is that if we increase the mass accretion rate, more amount of thermal energy will be lost in the form of radiation, so the disk should become thinner. However, we realize that the fact that the definition that is being used in this, which is being used like currently in the literature, is not a very well-defined definition. It's not incorrect definition, but it is not a very well-defined for the MAD simulation. For the same, it will remain the same. I will describe you what I mean by that. So what you see in here, this is on the right-hand side, I'm showing the density snapshot as a function of theta and phi for 4 mass accretion rate. The one at the top is -4, and the one, this is -5, -6, and -7. So this is density snapshot at one particular time of simulation at radius of 10 rg, and shown as a function of theta and phi. So what can be seen from the plot? So if we start from the bottom, you see that when the mass accretion rate is very low, the density filaments that we expect, which are the ones that are responsible for taking the matter towards the black hole, they are very thick, and they are kind of a very diffuse and not very stable. However, if I keep on increasing the mass accretion rate, what we can see from this picture is that the density filaments are becoming smaller and they are becoming more thinner. Now we want to understand we wanted to understand why is the case. Okay, and also here the red dashed line that you see is the equator region. So how is the density distributed along, like on the either side of the equator? Now, so what I said, the earlier definition consider the fact that, so what you this definition has pi by 2. This pi by 2 factor decides that the density is equally distributed on either side of the equatorial plane, and its maxima lies at pi/2. However, you can clearly see from this plot is that the density maxima always do not lie exactly at pi/2. So from that, we decided to measure the disk height using the maximum of the density. So from in this picture, we did not consider that the disk height is maximum at the red dash line, but rather measure the disk height by considering the fact that where the density maxima at that particular theta and phi lies. So from that, we define a definition where we measure the value of the particular theta, where theta is the maximum theta, where theta is the point where the density is maximum, and we divide it by the maximum of the density. Now from this plot, what you see on the right-hand side here, I'm plotting the for spin 0. There is a clearly contrasting difference between the low mass accretion rate and a high mass accretion rate. So as shown from the previous plot here, the density difference is not quite high, and the filaments are quite thick, and the gas pressure is also high. Therefore, you see that the disk height is quite similar for the low mass accretion rate. But immediately as I reach the higher mass accretion rate, when the thermal pressure is lost, the disk becomes much thinner. Now, this only tells us the fact that we expect the disk height to go lower if I'm increasing the mass accretion rate. But this still does not tell us why these filaments have to become thinner at high mass accretion rate. Why do they have to be thin compared to the lower mass accretion rate? So for that, what we decided to do is to simply look at the pressure balance inside the filament. So what I'm showing from the picture on the left-hand side is that I take a snapshot of the density in here. And at a particular radius, I take a circle and I I measure what is the pressure at the boundaries of those stars. And the star here represents my accretion funnels, or the accretion filaments, which are taking the matter towards the black hole. So how do I do it is that I take a particular radius, describe my accretion filaments, and I measure the peak of those points, or those star points, the pressure at those particular point, and the difference between those points as the area of those small filaments. That I measure by using FWHM, that is full width half maximum of those density peaks that you see on the right-hand side. And for the pressure, what we do is that we plot the gas pressure, the one which is on top, and the magnetic pressure, and the points where the gas pressure and the magnetic pressure crosses each other, that is where they intersect each other, we consider that as a point of this is the particular point where we measure the gas pressure. So the magnetic pressure. So from this point, we also have the magnetic pressure from here, and I have the gas pressure from here. I simply need to equate those two. Our analytical estimate, which I do not describe in here, says that the fractional area of the filament, that means the area that these filaments occupy at any particular mass accretion rate, goes as 1 over 4th power, 1 over the quarter power of P gas. So what happens is that at low mass accretion rate, the gas pressure is much higher compared to the magnetic pressure. What it means that we have the much larger filaments. I should not have written smaller. And for a higher mass accretion rate, the magnetic pressure is larger compared to the thermal pressure. So the filaments become more thinner. This is exactly the plot which is on the right-hand side. So here I'm plotting the pressure as a function of the area of those filaments. What you see is that for the low mass accretion rate, the pressure remains nearly the constant. And the moment I'm going to very high mass accretion rate, once I reach my critical mass accretion rate, the gas pressure reduces drastically, and Along with that, the magnetic pressure increases, which leads to the filaments which were earlier thick, now becoming much thinner filaments. The third important result that we found from our simulation is the behavior of the magnetic flux eruption. So if you remember, I described magnetic flux eruption as those events where the magnetic field on the black hole horizon reconnects and is getting thrown out, and the magnetic energy density is reduced onto the surface of black hole, and this process repeats. So if you look at the plot on the right-hand side, what I'm plotting in here is the MAD parameter, which I described earlier. That is the magnetic flux normalized by mass accretion rate. And here I'm plotting the results for the 7 mass accretion rate from no cooling at the very bottom to increasing mass accretion rate up to 10 minus 3.5 Eddington going at the top. So what can be seen from these plots is one very distinct feature is that when the mass accretion rate is low or when the cooling is off, those flux eruption tubes have a very smaller amplitude and their frequency is larger. However, when I reach a mass accretion rate of close to 10 minus 4, what you see is that there is a striking difference between these two pictures on the top compared to the pictures on the bottom, that the amplitude of the magnetic flux tubes now is much larger compared to the below mass accretion rate, and also their frequency decreases by a factor of 2. This raises the question of why is this happening and what is this actually? So for that, just to verify our picture, we plotted the flux density in all our simulation. So what you see from the picture in right-hand side here is that I'm plotting the density profile at a particular timestamp for the mass accretion rate from low mass accretion rate here at the bottom right to the high mass accretion rate at the top left. It can be clearly visible that when the mass accretion rate is low, the flux tubes, these highly like the bluish region, they are highly fragmented and they are smaller. However, if I keep on increasing my mass accretion rate, at the high mass accretion rate, those flux tubes are much larger and the density in the inner region of the disk is also large. The density is large because we increase the mass accretion rate, that is true. But one important factor is that we see that the larger flux tubes, that was also shown from this plot in here. This raises a good question. So we wanted to verify, so we did the same thing to understand what could be the reason for that. So we plot the plasma beta parameter, which I described earlier, that is the ratio of gas pressure to the magnetic pressure. And here also we see the same striking difference. And thirdly, we also plotted the magnetization parameter, which is basically the ratio of magnetic energy density to the rest mass energy density. Here also you see that when the mass accretion rate is low, the flux tubes are kind of fragmented and they are smaller. But if I increase the mass accretion rate, they become much larger in volume and occupy larger area. We explained this by the fact of these things. So it's a kind of a complicated picture, but I don't think it should be much. So what happens is that in magnetically arrested disks, the magnetic flux at the horizon and the magnetic flux tubes, the dynamics of the magnetic flux tubes are described due to 3 processes. So what happens is that the first is the magnetic reconnection. During the magnetic reconnection, magnetic field reconnects, the magnetic energy is lost. This lowers the magnetic flux onto the black hole, and the magnetic those flux tubes migrate outward because of the tension in the magnetic field lines. Now, the second thing is the advection of plasma as the frozen in magnetic flux, which happens towards the black hole. And this is primarily governed by the magnetic interchange instabilities that happens at the disk magnetosphere interface. And the third thing is, once those flux tubes are formed, now they move outward because of the magnetic tension, and their survival or the destruction is controlled by the Kelvin-Helmholtz instability. So there are three things: magnetic reconnection produces them, and the magnetic interchange instability leads is the one which is causing the flow of plasma towards the black hole. And once those flux tubes are created, they move outward, and their survival or how long they will survive depend on the Kelvin-Helmholtz instability. Now, what we see from the means our simulation is that cooling reduces the plasma beta parameter, which is obvious because plasma beta parameter is the ratio of the gas pressure to the magnetic pressure. So the gas pressure is going down because the disk is losing the thermal pressure in the form of radiation. However, it is known that at larger beta, the interchange modes grows faster. So what happens is that for a small accretion rate, the interchange modes go so fast that it leads to the magnetic flux tubes which are being created to not grow into a much larger, but rather get fragmented into a smaller flux tubes. Similarly, larger plasma beta, it also enhances the Kelvin-Helmholtz instability growth rate. So what happens is the magnetic flux tubes, they are getting easily swayed by the Kelvin-Helmholtz instability. Sooner they are being produced by the flux eruption event. Therefore, their lifetime is much smaller, and they extend only to a much smaller radius. And this is exactly the behavior that has been observed into the simulation. And we also verified the previous results that the synchrotron cooling, whether the synchrotron cooling is dominant or not. So what you see from the picture in here is that I'm plotting the electron temperature, synchrotron cooling, and the Bremsstrahlung cooling rate. And if you look at the color bar on the right-hand side, the synchrotron cooling, for the synchrotron cooling and for the Bremsstrahlung cooling, you realize that synchrotron cooling is much, much larger compared to the Bremsstrahlung cooling for the at any particular mass accretion rate. So it means we confirm that the synchrotron cooling is a dominant compared to the Bremsstrahlung. Now we also measured the radiative efficiency. So how we measure the radiative efficiency is simply integrating the amount of radiation, amount of the energy that is being radiated away, and we normalize it by the mass accretion rate, which we measure at 5 Rg. We expect that the cooling to change the efficiency because more cooling means more amount of radiation is being emitted from the disk. So for low mass accretion rate, the efficiency is very low, which is close to 4%. And this has also been verified from the simulation of 2 temperature plasma. So with our results also aligns very well. And for the very high mass accretion rate, its efficiency increases closer to 50% or even more. However, a very interesting feature that you see from this plot, which appears, is that here I'm plotting actually the cooling rate as a function of radius, and the radiative efficiency as a function of the radius. That what you can see easily is that at higher mass accretion rate, the radiative efficiency seems to start tapering around. Okay, so again, this was the result. This was the radiative efficiency that we plotted for a particular single spin. However, we decide to compare the radiative efficiency for the different spin. So let's look at the plot on the right-hand side. Here I'm plotting the radiative efficiency as a function of spin. So what you see in here is that the radiative efficiency starts to saturate for a higher mass accretion rate. It goes to around 50% or so. However, and an important factor is that for low mass accretion rate, the radiative efficiency for the positive spin is larger by a factor of 2 across the spin. So in order to understand why is the negative spin having the low efficiency compared to the positive spin, we looked at the cooling rate that we plot on the left-hand side as a function of the radius. So what you see from this plot is that here I'm plotting the cooling rate for the different spins for a particular mass accretion rate of 10⁻⁶ m dot Eddington, and the second is 10⁻⁴ m dot Eddington. A very distinct feature that is observed from these two sets of lines, the dashed lines and the solid line, is that for the low mass accretion rate, which is the solid lines, the difference between the separation between the two lines is larger compared to the separation between the two lines at the higher mass accretion rate, which is the dashed line. This happens because of the fact that low mass accretion rate has larger differences into the strength of magnetic field. So since the synchrotron cooling depends on the square of the magnetic field, if there is a stronger differences into the magnetic field, which means there is a stronger change into the cooling efficiency as well. That means, so this is the fact that, so the region that we observed, there is a difference into the efficiency at low and high mass accretion rate is because of the fact that the magnetic field for the low mass accretion, the magnetic field for the low spin is smaller compared to for the positive spin. Now, then we describe about the force balance. We do not need to go into the equations, but simply what we do is that we write the force balance equation as to how the disk is being held into the horizontal direction. Like, so what are the forces which are responsible for holding the disk in the horizontal description and horizontal direction? We have we describe the three components. We call them as the dynamical component, thermal component, and the magnetic component. And this is the way of averaging, though it is written in the code, which is not much of an importance. But the three important component is the dynamical, thermal, and the magnetic components. Now here I plot the radial force valence as a function of the, so here these are the radial forces. They are normalized to gravity as a function of the theta. So it goes from it goes from the South Pole to the North Pole. And so, and also the four subplots are the one, at the top left is for the low mass accretion rate, going up to higher mass accretion rate of 10⁻⁴. What you see, a very distinct picture as has already been seen previously, is that at low mass accretion rate, the disk in the horizontal direction is mostly balanced by the thermal pressure, because the thermal pressure is mostly the dominant component. However, the dynamical and the magnetic field components are smaller. I increase the mass accretion rate. The thermal component initially remains the same because there is not much of loss in the form of radiation. But as soon as I reach my critical mass accretion rate, here you see that the thermal component is much less because the disk has lost substantial amount of the energy in the form of radiation. Now, since the disk has to balance, along with that, the magnetic field is also increasing because the thermal pressure decreases, as I said earlier, and the magnetic pressure increases. And since the disk has to remain into equilibrium, another component has to increase, so the disk will be held in equilibrium. However, once you realize that from -5 to -4, the magnetic field component or the magnetic pressure is mostly this constant. However, the dynamical component, which is the inertia of the disk, the inertia of the matter which is flowing towards the disk, is increasing. That leads to the disk being held into the equilibrium. However, the thermal pressure becomes kind of negligible. The same picture can be seen at the equator. So earlier I was showing the whole picture from one pole to another pole. This picture on here, what I'm showing is that the same force balance just at the equatorial line rather than showing for all the angles. So here is the force normalized to gravity as a function of radius. a very similar behavior is observed, just like the previously I said. Thermal pressure is large at low mass accretion rate. If we increase the mass accretion rate, the disk is losing the radiation so the thermal pressure goes down and the magnetic pressure is increasing. So one thing that we realized from our result, so the bottom line of this plots or this force balance thing is that if I'm increasing the mass accretion rate, the thermal pressure is going down and the magnetic pressure is increasing. We did not go to a very high mass accretion rate, but our results suggest that if we go to a higher mass accretion rate, there will be a point where the disk will be completely held by the magnetic pressure rather than the thermal pressure. This is one of the other results, which is a bit partial. This is not 100% sure yet, but we also realize that cooling affects the black hole spin. So what we found that higher is the cooling, lower is the disk height because of loss of thermal pressure. And because of this, the disk will be more luminous, and this leads to the slowly rotating black holes. There has been study like last year, just a few months ago, where a group of Sasa Tchaikovsky have performed the simulation, but they targeted a particular disk height just to show that luminous MADS means the luminous magnetically arrested disk slows down the black hole, which our result support means which our results show without considering the particular height of the disk. So we self-consistently evolve the radiation, and so that when the luminous magnetically arrested disk slows down the black holes. Here is the summary and conclusion of my talk. So what we did is that we wanted to understand what is the effect of radiative cooling. That means under what condition radiative cooling is important or not. To derive the critical mass accretion rate, we use the fact that the gain of potential energy is same as the rate of loss of energy through the synchrotron. We use a simplified one temperature model of electron temperature, and we realize that we get a critical mass accretion rate at 10 minus 5.5 Eddington mass accretion rate. And what is its implication is that it changes the jet efficiency, also the magnetic field, and it limits also the limits of thermal pressure contribution. However, truthfully, I'm also describing the limitation of the work, because we're using, as Professor Agnieszka already said, using a fixed temperature ratio of the electron to proton temperature is only applicable in a very small range of mass accretion rate. This can be done with the inclusion of radiation transport, that is performing the radiative GRMHD with the 2 temperature plasma. And the reason for that is that because at low mass accretion rate, Coulomb coupling is inefficient. So in that case, we might overestimate the radiative efficiency. So that is it. And thank you very much.
Thank you.
Now I can.
Yes, we have a little time for questions.
Sure.
Yeah.
I'm very happy to.
Amit was first, so please, then Mikołaj.
One of the conclusion is Coulomb cooling, which
Can you be a bit more louder, because I hear you very lightly?
One of your conclusions is that Coulomb cooling is
Yes.
for the Bremsstrahlung. So
Yes.
if change the ratio, the electron to proton temperature ratio, so
Yes.
get the same conclusion.
About what?
Of
That if I use the different value of electron to proton temperature, will it remains the same or not? What is?
Yes, that's my question.
No, so the question is like, okay, so that I said earlier, people have used the value of electron to proton temperature ratio anywhere between 3 to 10.
Mhm.
And what has been realized from the results of the 2 temperature radiation GRMHD simulation is that let's consider if I use my results vary by factor of 2 to 3 if I go to a lower mass accretion rate. I did not go to a higher mass accretion rate because of the fact that I said earlier, in those mass accretion rate, the the Compton effect will start playing impact because the radiation backscattering will have a significant impact into the results. So we decided to stick our results only up to a particularly low mass accretion rate. I hope this is sufficient. If it's still there, I can answer.
Okay, yeah. Then the next question, Mikołaj.
Okay, so I'm not very much familiar with the topic of magnetohydrodynamic simulations.
Okay.
But I'm curious, what kind of so given this type of simulation, you're always assuming some kind of resolution.
Yes.
And this also means that you're making an approximation and using some kind of small scale physics. So my question, what physical phenomena you might be losing by performing your simulations this way? What kind of phenomena?
It's a very good question. So, okay, there has been studies where when earlier people started doing the simulation of GRMHD, there was a question of what is the minimal resolution where you can resolve the things that you want to study to a particular level. Besides, if you are below that, you cannot resolve the things. So means in the community at the current moment, what is like a kind of a standard resolution for resolving the things is that we have to have 256 cells in R, 128 in theta, and 128 in phi. So that is 256, 128 square in the resolution. This is the minimal resolution. Now, if you want to study the magnetic reconnection, which I think my sim results do not show here. Let me show in here. So if you look at this picture, so these regions that you see in here are these regions. These are the actual magnetic reconnection sites. And I can barely resolve in my simulation, which are 256Q. So if you really want to study the magnetic reconnection, you need to use the so-called method of static mesh refinement or adaptive mesh refinements. These are the methods which what it does is that you take a particular grid cell, and where you want to resolve more of your simulation, you simply aggregate more cells into that particular region so that you can have more higher resolution and you can study those impact of what are the changes, like where is the acceleration sites, where is the reconnection happening. If you really want to study the reconnection, you need to perform the simulation for a higher resolution. But if you're studying the global dynamics of the disk, anything about 256, 128 square is going to give you a sufficient resolution for studying the global dynamics.
Okay, thank you.
Welcome.
Piotr?
Thank you for a very interesting talk. I had question about the disk thickness, but you have answered all my questions. But my additional question is about the cuHARM and what type of spatial reconstruction do you use in your study, and what type of Riemann solver do you use?
So Riemann solver is HLLC, Harton, and I forgot the full name.
Yeah, okay, HLSC.
Yes.
And what type of spatial reconstruction? PPM, MinMod?
So I think we have 3 or 4, which I don't remember at the moment. I don't remember the names at this moment, but I can check it out.
Yeah, okay. Thank you.
You are having several options, right?
Yes. Yes.
Yeah, because the results from the simulations looks quite diffusive for me, even though your resolution is quite high. So I expected that this is MinMod. This is the reason why I asked this question. Yeah,
so I mean, we have had like something 3 or 4 different methods. It depends like which one we want to choose and which one is more numerically stable and faster. We decide to work with that one.
Obviously. Thank you.
You're welcome.
Bożena, last question.
Okay. It's a continuation of the question which Mikołaj asked.
Yes.
About the resolution, because magnetic field reconnection, as you said, is very important, but on the other hand, you do not fully resolve it.
Yes.
So how you account globally for the effect of magnetic field reconnection in your simulation? You have some coefficients to enhance what should happen, or no, that's the
So the answer is we do not do any kind of corrections in usual GRMHD simulations. There are studies which I'm not sure if you are aware, by Bar-Ilan and the other people working with him. So they have performed a simulation which is of extremely high resolution using adaptive mass refinement, which was something like 4,000 or 5,000 cube, like very high resolution. But what is more important to state in here is that it depends upon the problem that you want to study. I understand that resolving the reconnection sites is very important if you want to study the particle acceleration, like to understand where the neutrinos are being produced, what kind of a particle acceleration is happening there. But when it comes to like a global GRMHD simulation where you do not want to study like a particular impact of what is going to happen when there is a magnetic reconnection, you need to have a base resolution, which has also been studied previously. That what is this base resolution where your magnetic, the MRI, that is the with magnet, so the quality factor of the MRI will be strong enough so that you won't have to be worried about the simulation resolution. I understand the fact that simulation resolution is a very important factor and it does play an important role, but it depends upon the problem that we want to study. If we have to study just global properties of the disk, it is not much of an important as long as we have the base resolution higher than the resolution that we can resolve the magnetorotational instability. If you want to study more properties, like, as you said, the magnetic reconnection, we sure need to have very high resolution to have like proper resolving of the MRI. I hope this is sufficient. Otherwise, I can add to that.
Thank you.
Thank you. Yeah, it is sufficient, and we are already ending this colloquium because it's time to finish. So
Okay.
Thank you very much for your seminar, and I wish to see the paper which you advertised, this working preparation about extraction of rotational energy of the black hole by luminous magnetically arrested disk. So congratulations on your work, and thank you again, and thank you to everybody for being here. See you next time.
Thank you very much for inviting, and thank you all.
Bye-bye.
Bye-bye.
Take care.